Today we start a new chapter. The topic is tree-based methods, and as we will see, this is an approach quite different compared to those that we have been investigating so far. And the main idea is stratifying or segmenting the predictor space into a number of simple regions. And since the splitting rules that we are going to apply can be effectively summarized in a tree, this family of approaches is known as decision tree methods. And what are the pros and cons of tree-based methods? Well, there is a definite advantage because they are simple and useful for interpretation. As a matter of fact, if you want to communicate the results obtained by trees, you will find it much easier than communicating the results obtained by even linear regression if the people you are to explain your results are not expert in the field of statistics or learning. However, there is a price to pay for simplicity. As a rule, they are not as competitive as other methods that we could apply to solve our regression and classification problems. However, in this chapter, we will also see that there are methods that use trees that goes under the name of bagging, random forest, and boosting, that by growing multiple trees can be rather effective and competitive with more advanced methods that we have already seen and that we will see later. However, by combining multiple trees, there is the problem that the advantage of a simple interpretation is going to be lost. Okay, so in their simple form, they are very easy to interpret, but you lose something in performance. If you want to improve your performance, then you can, but the price is that this will be at the expense of some possibility of explaining or interpreting your results. So let's start with the basics of decision trees. They can be applied to both regression and classification problems, and we will start with regression problems, and later we will consider also classification ones. And we start with a simple example. These are baseball salary data, okay, and we would like to stratify these data in some sensible way. So before starting with the tree, we start from the data and we try to do this by ourselves. Okay, and let's explain the meaning of the data. So these are each dot is a baseball player. On the x-axis, you have the number of years he's been playing in the league, and on the y-axis, you have the number of hits. Okay, so of course, you can think that the more hits, the better, of course, and the color represents the wage of the player. So the hotter color, the higher wage. Okay, if you had to stratify, so to in some sense classify this data, how would you proceed? Well, if I look at the data, I can see that there is a stripe here of low salary players, and it seems that although hits has some relevance, the important decision variable is years. So if you are playing in the league since a few years, it is the case that your salary will be not too high. And so this could be a first decision, something like something less than 4 years, maybe 3 years, something like that. So below 3 years, I can see a category of low wage players. Then I have the remaining ones, and here instead you can see that number of hits is really important to predict the wage. So if a number of years is greater than 3, say, let's say 3, yes, 3, 4, if it is greater than 3, then I would look at hits, and then this could be something about 100. So below 100 hits, you have a medium-low wage, and over 100 hits, you get the high salaries. So this is the interpretation that we could give just looking at the data. So below 4 years, 3 years, low salary. If you are above 3, you are above 3 years, you are in this region. Here the number of hits becomes more important, and about 100 hits can divide the players between those that have a medium low wage and those that have a rather higher wage. Okay. And this can be done automatically by means of a tree. And in particular, by applying a tree method, you would find this result. You have a first splitting, which is based on years, and precisely if years is less than 4.5, you have a first category, and a second category if years is greater or equal to 4.5. And here you have a leaf. This is called a leaf, and this is the average wage that you expect for those that have less than 4.5 years in the league. Okay. On the other hand, if you are in this branch of the tree, then you have a second split, and this is based on hits. We had said that roughly it was 100 the critical point. The automatic algorithm found 117.5. And again, if your number of hits are below this threshold, then your average wage is 6. And if you are above, this is 6.74. If I remember well, this is not proportional to the wage, but there is a logarithmic transformation for this data. So the automatic rule, the automatic algorithm gave results that are in accordance with our heuristic assessment. Okay, yes, log salary. Here you can see that we are talking about log salary. And so we had a regression tree that was fitted, and when you have a label with the inequality, this means that you have a split, and that on the left you have the case when you are satisfying the equality, and the right branch is the one for the equality not being satisfied. And okay, this is explained what we have already said. And this tree has two internal nodes, the tree that we have just seen. Okay, and okay, you can see 1 and 2 internal nodes, and 3 terminal nodes or leaves. The terminal nodes are 1, 2, and 3, and these are called leaves. It is the case that this is a tree where the leaves are at the bottom and not at the top. So usually you think of a tree as something that grows from the ground and goes to heaven, goes to the sky. And but the typical way decision trees are represented is bottom up. So you start you start from the top and you go to the bottom. Okay, so this just to know. And the number in each leaf is the mean of the response for the rest of the observations that are in that leaf, that refer to that leaf. And it's important to note that all your data are eventually assigned to one of the leaves. So in this very simple tree that we have been estimating, eventually all the players will be assigned to one of these 3 leaves. Okay. Here you can see again our tree represented on the scatter plot of the data. Here you would need a 3-dimensional scatter plot, and as a matter of fact, in the first plot we had different colors to suggest the 3rd dimension. The 3rd dimension is the response, that is the wage of the players. Okay, so you take a first splitting here, 4.5, and so you have this region R1. Then you analyze this second region, this big region, and you decide that the good splitting is this one, made on hits, and you obtain regions R2 and R3. Okay. Some terminology. We use this tree analogy, and according to this terminology, the regions R1, R2, and 3 are known as terminal nodes. And okay, I have already said the trees are drawn upside down, so the leaves are at the bottom, and the points where the predictor space is split are referred to as internal nodes. In this tree, for the hitters, the 2 internal nodes are indicated as ears less than 4.5 and hits less than 117.5. Okay. What about interpretation? At the beginning of this lecture, we said that a definite pro of decision trees is the ease of interpretation. And here we can see this quite clearly. Years is the most important factor in determining salary, because you see that this is the first splitting rule, and as a matter of fact, players with less experience, with a few years in the league, are going to earn lower salaries. Then, when you are playing for some years in the league, okay, for the young players, the number of hits is not that important. But if you are playing for some years in the league, then the number of hits is going to affect salary in a significant way. And of course, players that made more hits are going to have higher salaries. Of course, this is really simple, okay, but compared to, for instance, a linear regression, it is clearly easier to understand and easier to communicate, of course. Let's go now into some details about the tree building process, and we have steps. So, first step, so the first step, the key point is dividing the predictor space into distinct and non-overlapping regions. So as a matter of fact, we are partitioning the predictor space. So the space where the predictors live, this is partitioned in regions that cover all the space and are distinct. So the intersection between 2 of them is empty. And the idea is that for every observation falling in one region, we will make the same prediction. So once we have the regions, we will find what is the best common prediction for all the cases falling in that region. And this prediction is just the mean of the response values for the training data, the training observations that are in the given region. Okay. With these principles, in theory, you could consider regions of any shape, but in practice, we are using always regions that are rectangles. Of course, we are speaking about rectangles in higher dimensions, so they are high-dimensional rectangles, or if you like, we can call them boxes. And we are doing this because it is much simpler, both for the estimation and the interpretation of the final results. So our final goal is finding boxes R1, Rj that minimize the residual sum of squares, because we are talking about a regression problem, so the final goal is always obtaining the smallest RSS. And this can be written in this way. So the idea is to find boxes such that the sum of the squared residuals in this is the sum of the square residual for some given Rj box, and then I take the sum with respect to all the capital J boxes. So in the end, I want the sum of the squared residuals to be the smallest possible, and here the predicted response is just given by the mean response for the training data that fall within the jth box. Okay, it would be nice if we could explore all possible alternatives for the boxes that I can define in my predictor space, but this is computationally impossible. So you can imagine so many boxes that you cannot go that way, and this is not feasible. So rather we follow a top-down greedy approach. A greedy approach means that we are proceeding step by step, and at each step we are making the decision that gives the greater gain, even if it could be that this decision is going to make it impossible to explore other decisions that would have been better, but do not give an immediate gain in the iterative procedure. And this greedy approach is known as recursive binary splitting. It is a top-down approach because we start at the top of the tree, and we start splitting the predictor space, and each split is going to create two new branches that go down. So we start from the top, we have a first split, so we have two branches, then we will decide if either of these branches has to be split again, and so on. This approach is greedy because at each step we are choosing the best split without looking ahead. So it could be that a split that it is not the best one immediately is going to lead to better results in the long run. So when you go on in your recursive building of the tree. But of course there is a computational problem, so this greedy approach is a practical way to address the computational issue I have told you. Okay, let's go on with our details. So we first select the predictor xj and the cut point s, a threshold, such that when I split the predictor space in these two regions, so the regions where the x is a vector of the predictor, so the set in the predictor space such that the jth variable, the jth predictor variable, is less than s, and this is the other region, the set given by the set in the predictor space where the jth predictor is greater than or equal to s. And of course we have a number of possible choices. So if we have p predictors, I will have to consider each of them one at a time, and for them I will have to look for different choices of the threshold and see what's going to happen. So I start from the first predictor variable x1. I consider the possible splits on this variable. For each of these splits, I assign values to the leaves. I compute the RSS, and I just take note of this result, and then I go on with the second predictor variable x2 and so on, and in the end I will choose to split the predictor variable that is going to give me the greatest reduction in RSS. Once this has been done, I can repeat the process, of course. So nothing has changed. So I can go on in the same way. So I have all the predictor variables as candidates for being split, and I explore each of them. For each of them, I found the best possible split threshold, the cut point S, as we call it, and in the end, I choose the split that produces the greatest decrease in RSS. Okay. Uh, there is a difference in the second, third, and fourth step with respect to the first one. In the first step, I am splitting the entire predictor space, while in the subsequent steps, I have to split just one of the two regions I found in the first step. So when I go on with the procedures, the splittings that I consider are splittings of the temporary leaves in some sense. So at some point I have temporary leaves, and I consider splitting them. So I split just these sub regions. Okay. And so let's summarize. I start, I make a first splitting, I have two regions. Then I consider splitting either of these regions, and I find what's the best split. So I will split one of the two regions. At this point, I have three regions because I have one region generated by the first split, and the two further regions generated by the second level split. And I can go on as long as I want. Usually, you will not arrive at the point where each leaf contains just one observation, but you will stop before, for instance, when no region contains more than five observations. Okay. What about predictions? Okay, we can predict the response for a new test observation just looking at the region where this test observation is going to fall, and then we will use as prediction the mean of the training observations in that region. Let's see an example. Okay, this is a five region. The first plot in the upper left corner is just an example of a partitioning of the predictor space that is not possible by the tree method. So by using trees, this is something that cannot be achieved. Rather, you will achieve partitioning that a partition that could be of this type as the one that I am indicating. And here you can see how the splitting was obtained. So the first decision was made on x1 with the cut point t1. So I divided the entire space into two regions. Then the second splitting was on x2, and it was done on the left branch. So here I had divided the predictor space in two parts, on the left and on the right. I have found that the best was to split the left branch, and it was was split using T2 as cut point, and so I divided this subregion into R1 and R2. Then we go on. A further split is made on X1 again, so it is done on the right branch. This right branch corresponds to this rectangle, all right? And it was found that the best split was with cut point T3 for the first variable x1. So this is T3. If this is the cut point, I have two further subregions, R3, and here there is another subregion on the right of T3. And the next and final splitting is on the right branch, so it means that this was the region, this rectangle was split, and it was split according to the second variable x2 with cut point T4. So here is T4, and therefore now you have this rectangle that now is split into two subregions, R4 and R5. And it is very nice also to look at this three-dimensional representation, because here you can see the function that you are estimating. So the idea is that in each of these regions, the response prediction is given by the average of the observations that fall within that region. So maybe that this is the average of the observations falling in R2. This is the average of those falling in R1. This is the average of those falling in R3, and this is the average of those in R4, and this is the average of those in R5. And so you can see that this is a quite strange surface. So it is not continuous. So it is a piecewise constant, we could say. And this is the function that you are going to obtain. Recall that here you have a regression problem with two predictor variables, x1 and x2, and therefore your final goal is finding a surface. So f, the regression function, that is a function of x1 and x2. So your final goal is to find a surface, and this is a way to approximate a surface by means of a piecewise constant approximation. For some purposes it could be good. For some other purposes this could result quite a rough approximation. It depends on the application. Of course, it's very simple to explain. So because you have a set of rules, and in many fields, think about medicine, for instance, practitioners have a way of approaching problems that it is often rule based. So in this case, you would offer some prediction method that is well in accordance with the way they are accustomed to think about problems. So here are the details of the previous figure. I think that I have already explained everything, so we can go on without problems. Okay. There is an issue with the fact that we, using the procedure that we have outlined, you are going to produce good predictions on the training set, but you are likely to overfit the data. So that in the end your performances on the test set will not be adequate. This is quite natural, because if you don't have a stopping rule, the leaves of your tree will grow in number, and eventually you will be able to follow quite closely your training data. And you know that if you follow the training data too closely, then you're going to learn the noise. So this is the usual problem we already know. So how could we avoid overfitting in order to have better better performances on the test data. So the idea is that a smaller tree with fewer splits, that is fewer regions, has less degrees of freedoms, and this might lead to lower variance and also better interpretation, of course, because the number of rules is decreasing at the cost of little bias. So one may think of an alternative process where you grow the tree only so long as the decrease in the RSS due to each split exceeds some threshold. So the idea is that I put a limit, and I want that when I create a new branch, then I should improve my RSS by some minimal amount. This will produce smaller trees, but it is a kind of short-sighted strategies. So in this way, I will give up some splits early in the process because they don't seem valuable. But it could be that there were further splits that I never reached because I stopped before, that were really worth. Therefore, this is a kind similar to stepwise procedures if you want, but for this reason there is another approach, and the approach is based on the idea of pruning. So we are still using the metaphoric image of the physical tree, and so pruning means that you are cutting some branches, and this is what a gardener we will do to have a stronger plant. And the idea is I will grow a large tree, we call it T0, and then we will prune it in order to obtain a subtree. And the idea is that the subtree will be more robust. Having grown a large tree, this means that some splits that were useful, that I would not have reached if I stopped my procedure too early, will be reached, and so I will sacrifice only branches that are not that useful. So this is the idea behind pruning. And we, in particular, we are talking about cost complexity pruning, which is also known as weakest link pruning. And the idea is to have a sequence of trees indexed by a non-negative tuning parameter alpha. So we need to introduce alpha, and alpha is part of a complexity penalty. So instead of considering, as I did before, just the sum of squared residuals, here I add a term that is alpha times the number of terminal nodes. So the idea is that if two trees have the same residual sum of squares, I will choose the one with less nodes. And even more than that, it could be that I prefer a tree with worse residual sum of squares if the number of terminal nodes is much smaller. So it is so simple that even if it explains a bit worse the data, I prefer it. This is somehow similar to complexity criteria that we have already seen at work, of course, like the AIC or the CP criterion, where you put together a complexity penalty with the residual sum, with the usual residual sum of squares. And the idea is that if I take a given alpha, I can consider possible subtrees, and I can rank them according to alpha, and for each alpha, we'll find a subtree that optimizes this cost function. This means that depending on alpha, I will have different optimal trees. Here, the meaning of the sum of squares, I think it's quite clear. This is the sum of squares for a given region, for a terminal node, and here we are considering all the terminal nodes with the constraint that we are not going to exceed the number of terminal nodes of that tree, which by definition is indicated in this way. This is the cardinality of the set. Okay. And I think, all right, here we are. So the tuning parameter controls the trade-off between complexity and fit to the data. And most importantly, we can tune this alpha. We can find an optimal value that we call alpha hat using cross-validation. At that point, when we have found the optimal alpha, we will go back to our data set and get or choose, select the subtree that was associated with alpha hat. So this is a summary of the algorithm. Okay. This is a summary of the algorithm, and sorry. We use recursive binary splitting to grow a large tree on the training data, and we stop only when each terminal node has less than some minimum number of observations. So we have a large tree. We don't worry about overfitting at this stage. Then we apply cost complexity pruning to the large tree in order to obtain a sequence of best subtrees as a function of alpha. So we take different values of alpha, and for each alpha we find the best subtree. So the subtree that optimizes that cost function that we have already seen. So I select alpha, then when I have selected alpha, I can consider different subtrees. That is, I can prune branches and look for the best pruning strategy. And so I get a smaller tree that has the property of optimizing this cost function for that given alpha. Now, however, I need to select the value of alpha, and then I do this by k-fold cross-validation, and I proceed in this way. So for k equal 1 to capital K, I repeat steps 1 and 2 on all my training data, but 1/k. So there is 1/k of the training data that are kept apart. So I work on k minus 1 over k kth fraction of the training data. I evaluate the mean square prediction error in the left out kth fold, okay, and I do this as a function of alpha. Okay, so I'm repeating this procedure for different values of alpha. So for each value of alpha, I'm going to find an assessment of the mean square prediction error. At this point, I will pick alpha to minimize the average error. Of course, I have to average over the k folds. When I'm done, so I have the optimal alpha, I will go to step 2, where I have my collection of best subtrees. So for each of the considered alphas, I have the best subtree. I found what is the best alpha, and then at this point, I have the optimal subtree. I think we can stop here for a pause.